All right, good. Today's the 13th. Only 12 days till Christmas. Who'd have thunk it, right? Oops, I'm on the wrong tool. There you go, big guy. So what is it? It's time to buy your math teacher a present, did you say? Is that what she said? I don't know. Something rad. Uh-huh. Today we are going to learn about independent and dependent probabilities. So super easy. And I have one worksheet for you and another one that's kind of in the works. I'll probably just give you the one today, and then the other one is still like in edit form. So I don't like the vibe of it, the look of it, the formatting of it. So I'll probably put a little more work into it and then get it to you. Yeah. So anyways, what we're doing is these are, by the way, technically, these are both called compound probabilities. So a compound probability is when you want more than one thing to happen. And so there are two types of compound probabilities. One of them is called independent and one of them is called dependent. So I say if all goes well, this shouldn't take all too long. So let's talk about the easy one first. Let's talk about independent. It's always easier. So when we talk about independent probabilities, in fact, instead of calling them independent probabilities, why don't we, for this section of our notes, just call them independent events? So when something is independent from something else, it basically just is not affected by that something else. And so an example of two independent events would be like, let's say you rolled a die. And like I said the other day, just assume from this point on when I say die that I'm not talking about some 20-sided Dungeons and Dragons thing. Like a die is assumed to be a standard 6-sided. They call it, some math books call it a number cube. I just think that sounds weird. So I just number cube. So I just call them die. It's a die. So if you were to roll a die, right? You okay, buddy? Okay. And then flip a coin. This is an example of two events back to back that are fully independent from each other. What I mean by that, and this, by the way, this explanation will make more sense when you see what dependent events actually are. But let's say I were to roll a die and it lands on a 4 or a 3. Does the coin care what I got? Is what I get on the coin affected in any way by what the die did? No. So that makes them independent events. So like if I said this, if I said, what's the probability if I roll a die and flip a coin that I get a 4 and then heads? These are independent events because, again, the first one happening or not happening has no bearing on the second one happening. So the way we are going to do these is multiplication. Whenever you have stacked like back to back or back to back to back probabilities, then you just multiply their probabilities along the way. So let's attack them in pieces, one by one. What's the probability, first off, that the die lands on a 4? Good job. So we write 1 out of 6. And remember, there's 6 things that can happen when you roll a die. Only one of them is named 4. What's the probability if I flip that coin that it lands on heads? 1 out of 2, 1/2. And now the key to this is going to get you through probably the next couple of days, is this. You have to, I already said it, you have to multiply those probabilities together. Okay? So overall, if I said to you, what's the probability if I had a die and a coin and I went roll flip, what's the probability that in order it would go 4 heads? The probability is overall 1/12. And we just take and how I got that, in case you're interested, is I just went 1 times 1 is 1 and 6 times 2 is 12. So that's a real simple example of independent events. Here's another example of independent events. Let's say you flip 5 coins. So say you reached into your pocket and grabbed 5 quarters, or it could be 1 quarter and you flip it 5 times. Honestly, it doesn't matter. But if you go through the action of flipping either a coin 5 times or 5 different coins all at the same time, the explanation is still the same. Does any flip of the coin give a hoot what the flip did before it? No. So if I flip a coin 5 times, or if Trinity takes out a handful of coins and flips all 5 at the same time, we could answer a question like this. What's the probability that all of the coins land on tails? And the answer is going to be, this is how I'll tell you, I always expect you to set up probability questions like this. And some people are pretty rebellious and they don't, but here's what I do. I put a fraction and then a time sign and then a fraction and then a time sign and then a fraction and then a time sign and a fraction and a time sign and a fraction. That was a lot of, I'm surprised I didn't stumble over my own words. The reason I have so many fractions is because I'm doing this experiment 5 different times, right? So they're each a half. And there's other ways you could have written this, but as far as teaching this to you, the easiest way for us to see it is this. Each one is independent from the others. So the probability of the first coin is a half. The second coin is still a half. The third coin is still a half. The fourth coin is still a half. And the fifth coin, again, they don't care. Coins are unaffected by their, like, what happened before. That coin doesn't look at his homie and go, well, that guy landed on heads, I better land on tail. It don't work like that. So overall, what's the probability if Trinity pulls out a pocket full of 5 quarters and she tosses them all on the table? What's the probability that they all land on tails? 1 out of 32. So remember, we are multiplying. So 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Got it? You're going to see independent events all over the place. And so let me show you another example. Let's do this. And I'm going to do it without colors so that you guys can get it into your notes. Sound like a deal? Okay, so let's do just letters. Let's just go with A, B, C, D, E, F, G, H. So why don't you guys just, so I say I would normally do this part of the lesson with like colors, but to make your notebooks better, let's keep it so that color is not a requirement here. So let's say that I took those 4 letters and I put them on like little tiny, like Scrabble tile-y kind of things, and I put them into a hat. So here you're going to learn the difference between independent and dependent events, and you're going to see the following word used a lot. Replacing. So just stop and for a moment and think about what I'm about to say. And if it doesn't make sense, as always, just tell me that this doesn't make sense. But let's say that Peyton reaches into, so again, I put these 8 letters onto little tiles or cards and I put them into a hat and shake them around. So what would be the probability if Peyton reached into the hat that she would draw the A and then she would draw a consonant? And what is a consonant?
Anything that's not A.
Yeah, if it isn't a vowel, it's a consonant, right? So like the B, C, D, F, G, H, those are consonants, right? There's vowels and consonants. So if Peyton reached into the hat and grabbed out a tile, what is the probability that it comes out as an A? Yeah, correct. This is the part of the lesson where if I've zoned you out, come back to me, because this is what you really need to hear. Is the difference now is the question becomes, well, Mr. Ahern, did she put the A back in after she drew it out, or did she put it on the table over there? That question is where independent versus dependent comes into play. Let's say for the sake of this first example that she is doing this with replacement. What that means is Swaggy P over here, she reaches in there and she grabs the letter A. It's a success. We always assume in probability questions for it to make any sense that if we're going to plow on and answer the whole question, we have to assume that everything is happening successfully along the way. So Peyton has reached into the hat. She grabbed her first tile and she's like, booyah, it's the letter A. Let's say she takes that letter, pats herself on the back, and drops it back in the hat. The condition of the hat is the same as it was before, right? Good. So this is important. So the probability of her getting a consonant is something still out of 8 tiles, right? Because all 8 are back in there. Because Peyton said, I'm dropping it back in. That's what replacement means, is she's putting it back before she moves on with the problem. Like Micah said, yes, we look now at the state of affairs here, and we see that in the hat still looks exactly like it did before. These 8 letters are still mixing around in there. And Micah says there's 1, 2, 3, 4, 5, 6 out of 8. And so our second probability, or Peyton's second probability, is 6 out of 8. Still with me? So we would reduce that down. You can't do too much with it. You could take this, like this 6, and make it a 3, take this 8, make it a 4, and overall her answer would be 3/32. So exactly 3 times out of every 32, if Peyton goes, grab one, put it back, grab one, she should get an A and then a consonant. Everybody okay with that? Now, let's do the exact same problem again. Only this time, let's do it without replacement. This is it. If this makes sense, then you really pretty much get the gist of all of this. And these are now going to be dependent events. As soon as there's no replacement, then we can call this now. And you're
keep that letter out then?
You keep it out, and you're old enough to understand why we use that word. Like the second probability now is it depends on the first one, right? Like it's affected by the first one. So the questioning is still the same. So if I return the hat and it's still in its like virgin state there, and it's got like all 8 tiles, it's got the A, B, C, D, E, F, G, H, and all 8 are still in there, right? And Peyton reaches in and grabs a tile, what's the probability of her getting an A? Can we agree that it's still 1/8?
Mm-hmm.
But this is where it gets interesting. You got to be a kind of a smarty, visual, hard-working person for this. Peyton grabs the A, she pats herself on the back, but she sets it over on the desk. So there's some things that get affected here. First off, how many tiles are left in the hat? 7, correct. And how many of them are consonants? 6. So this answer is going to be different. If I cancel out this 6 and this 8, I would get 3 out of 28, which is a completely different answer. FYI, the same 2 events, replacing versus not replacing, are just never going to come out to be the same answers. Like it doesn't work that way. Let's do that same problem again, but let's do the probability of A, then valve. So let's do this problem twice. Let's do it with replacement, and then let's do it without replacement. So same thing. I don't know that I need to draw it again. We're still doing the simple example, 8 tiles, A, B, C, D, E, F, G, H. So in its untainted, like its brand new state, what is the probability that Peyton will reach in and grab out the letter A? Good job. And if replacement is happening, then she looks at it and says, booyah, puts it back in. What's the probability of her now drawing out a vowel? 2/8. You wouldn't, because she put it back. And that's the key, is if you replace it, then the tile bag goes back to being just the same as it was before Peyton started mooking with it, right? So if we reduce this down, reduce the 2 down to a 1, reduce that 8 down to a 4, we should agree that it's 1/32, correct? Now, the reason I wanted to do this one with you is because, well, you'll see that the top and the bottom are both going to be affected this time. Last time, it was only the bottom number that we had to drop by 1. This time, if Peyton pulls out the A and sets it over on the nightstand or something, she's affecting not only the overall number of tiles in the bag, but she's also affecting the number of vowels in the bag. So you kind of get the double whammy on this. So here we go. No replacement this time. If Peyton grabs out the letter A, the probability of that happening is, as it always has been, 1 out of 8, right? Because there's only one A. She takes the A. She sets it on the nightstand. I'm going to move back up now so I can illustrate on my ghetto little diagram. I hope you understand that this A is now out of the picture, right? So if she reaches back in the bag now to get a vowel, what is the current probability of that? 1 out of 7. So by tampering with the bag the way she did, she not only affected the overall number of tiles, we're down to 7, but she also affected the overall number of vowels. We're down to 1, you see. So the probability changes drastically. It's almost twice as bad or half as good. Yeah, it's 1 out of 56 now, right? So as you go through today's work, I feel like I could probably be done now. I don't want to talk you to death. But bear in mind that you need to read carefully because some problems will say, like, you do this and then you replace it. And then some will say you do not replace it. That is it. That is a massive difference as to how we approach the problems, right? All right, cool. I will leave the recording going and I'll just pause it. And if someone has that in that question where I go, oh my God, I should have said that, then I can just unpause.